It's essentially saying that like because 1 is an invertible, but 0.9 repeating would be revertible.
Well, 0.9 repeating
is 1, I know, but I'm saying like in like 0.9 repeating up to a certain point.
Just the 30th place.
Yeah.
No further, yeah.
That is invertible, so we should we should just say that 1 is invertible, or our basis should just
we
essentially be that 1 is invertible. Is that what it's saying?
Are you asking me what the proof is saying or what the theorem's saying?
There exists an invertible basis of the algebra, which would mean if we had to use 1, we could just use the closest thing to 1 and build a basis from that instead. Which would be almost like null because it's so close to 1.
So you're actually interested in making 1 an element of the basis.
Yeah, like 1 is just like what I'm saying. Because
I think
as some point that is
that's
what I'm saying.
I don't know. It's been a while since I thought about that, but I think that's not unreasonable. Like, take the basis you're given.
Yeah. If there's something that's not invertible, just get the next closest point, and it should be almost identical to 1.
Well, there's never a next closest point in a vector space, right?
Depends how you define it, but yeah. I mean, if it's a subset of the reals, then that would be a very close point. That would be almost.
As I'm talking to you about all this, I can give you a little bit more of the proof that I haven't written down.
Okay.
So what you could do. All right. So first of all, at this point in the discussion, I haven't really fixed a notion of distance.
That's
for
true.
one thing. So let me just tell you something.
Yeah, and hyperbolics are even weirder.
Well, the hyperbolics, I'm falling back on our previous notion of distance and plane.
It's not Euclidean because I remember you were talking about the geodesic of the
hyperbolic. Yeah, but that is divorced from that. Like I am not doing anything. No funky geometry here. It's just plain old Jane metric topology.
Okay.
And by that I mean this. So if beta is the basis for A, and we have x equals to like C1 V1, Cn Vn, Cn Vn, then the norm of x I would just define to be the square root of C1 squared plus Cn squared.
Why? Why?
Because I can. And the distance from x to y would be the norm of y minus x.
What is the norm then?
I'm defining the norm.
Okay.
The norm is the length. I'm giving a definition for length of a vector in the algebra. Now, what I'm telling you is this is a straightforward exercise in linear algebra. You can prove that this norm is in fact a norm.
Well, you're defining this as a norm and then saying, what does a norm mean like mathematically?
There are 4 properties. Right?
Okay.
So the properties of a norm for a vector space, right? A is a vector space, so I'm within my rights here, right? Mm-hmm. There's a few different properties. I forget the usual. So first of all, the norm of a constant times a vector is the absolute value of the constant times the norm of the vector, right? That's one thing. 2, the norm has to have the triangle inequality, x plus y is less than or equal to the norm of x plus the norm of y. And 3, you have to have that the norm of x is greater than or equal to 0, and the norm of x is equal to 0 if and only if x is equal to 0. So sometimes I separate those to 3 and 4 x. I think that's it. Unless I'm forgetting something. So we should go out and cook the hamburgers pretty soon?
Yeah.
Okay. I'm about to go out here. We're near the end of this.
Distance. Properties are that you can take the constant out, the absolute value of the constant out.
Right, now, the definition I've just written, it makes the length of everything in the basis beta what?
1.
Yeah, indeed. So it makes everything in the basis have length 1. And of course, in the context that the basis is the standard basis for Rn, this ad hoc basis, this ad hoc norm, you might call it, becomes the usual Euclidean norm. All right?
Yeah.
Once you have a norm, you can define open set, closed set, limits of continuous functions, like multivariate limits, all that. Okay? And I needed that to define adifferentiability. Because adifferentiability was defined in terms of the limit of a quotient of norms. That is this, I mean, we have to have a norm on the algebra to make sense of that adifferentiable.
Yeah.
Right? Before you can even talk about adifferentiable, technically you have to talk about continuity. Just like in calculus, we have to talk about limits before we talk about calculus.
Yeah.
Because limits are needed to discuss continuity. My point to you is just this: we can define a norm, and then here's where it gets interesting. You're like, well, how do you know that's the right norm and not a different norm? Well, this is the cool thing. In finite dimensions, the topology generated by one norm is the same as the topology generated by any other norm. So the metric topology on the norm is independent. Metric topology on a finite dimensional vector space is independent of your choice of norm.
Okay.
It didn't matter. You could use your fundamental, like, circles.
Mm-hmm.
Could be circles, they could be diamonds, they could be squares, they could be blown out diamonds. It doesn't matter. They all generate the same notion of open sets. You can almost see it, because if you have a point that you can put a little circle around, you can just as well put a little diamond around.
Oh, is it kind of like how the Euler characteristic, it doesn't matter what you do with it, the shape, it's always still going to have the same thing?
Kind of. I mean, that's a similar phenomenon, I would say. But anyway, my point is just that, yes, this is an ad hoc construction. Like, you have infinitely many choices of bases, so like, how is that okay? Well, it's okay because the limits that we ultimately define in these norms are insensitive to the choice of norm. So like, we can make any choice we want. Now, other people would say, well, this is a bad choice because it's divorced from the algebraic structure. And they're not wrong about that. This has nothing to do with the multiplication of the algebra. So I'm at the base level divorcing analysis from algebra in my viewpoint by doing this. Now, if you were to pick a norm which somehow interfaced with the algebra more nicely, you might get dividends on that. You might gain certain benefits. And we'll talk more about that as we go on. But at a base level, there is a norm, it exists, you can use it, you can define it. And with respect to that norm, the group of units is dense. And so what that means is you can take all of these, calculate the distance between each of these pairwise.
Yeah.
Right? They, none of them can be equal, so there has to be a finite distance between each one of those, right? Let whatever that is, pick the minimum of all those. It's a set of finite numbers, you can pick the minimum, right? Mm-hmm. So you pick that minimum, let's call it m. Then when you're replacing your first non-invertible element, you make sure that the inverse element, the invertible element that you pick, is less than m over 2 distance from the original one. Then you ought to be able to make arguments that show that when you replace that from the others, you haven't inadvertently. See, that's not enough either, because you got to worry about multiples of the elements as well.
Yeah, but I thought you can get rid of that because of the norm. You can take it out, even if it's multiple.
Yeah.
So you can just say this.
See what I'm just thinking about now. You see, even that proof is too naive. Oh, but it's intuitively clear that you can pick something infinitely close to your original thing, so it should be that the resulting basis can be made to be invertible.
Yeah.
See, here's the problem. I was just thinking, like, if I have this, right, and I've got, you know, this guy is my other one, and suppose this one happens to be, and suppose that V1 is an element of the zero divisors of A, and here's your V2, right? And I'm saying, okay, so we modify V1, right?
Yeah. That wouldn't be a zero divisor anymore.
So we pick something that's not in the zero divisors, like over here. Let's see if I can. Let's see if I can. Let me make V2 longer. Right, so I pick. Here's the problem. So this distance is what I'm saying is that M, that there's only one thing to worry about, right? So you pick something that's within M, less than M over 2, right?
Mm-hmm.
And let's suppose that I had written it more. Fine. So M over 2 would be like that, right? And suppose that I won't get to the point eventually here because we got hamburger stick. I'm gonna get trouble now. So anyway, V2. My point is, suppose I pick for my modified V1 like this line, you know, V1 bar. Right. So it's not V2 because V2 is further away.
Yeah.
But it happens to lie on the line of V2. Or it happens to be, I mean, V1 bar twice V1 bar or whatever is V2, or maybe it's twice, maybe it's 3.
Oh, I got you. Yeah,
maybe it's 3 times it. I don't know, whatever.
Yeah. Uh-huh.
That's a problem. See, because then my modified basis.
Oh, then you'd have zeros in that one too.
my modified basis would be invertible.
Yeah.
Well, it would be a set of invertible vectors.
Yeah. But then it would have something in there that wouldn't be invertible too, right?
Well, the trouble is it wouldn't be a basis then, because if this is you know if V2 if this is 3V1 bar.
Oh,
this is a linearly dependent set.
Yeah.
So it's more complicated than just finding the minimum distance between the basis and picking something closer than that.
Yeah.
Because I still need to worry about, once I pick that thing, is it actually a scalar multiple of any of the vectors, right?
Oh, yeah.
Probably I need some sort of horrible induction argument, which says, there probably needs to be like an induction argument which is based on, you know, suppose you've created you've made a basis so far, then try to make the next step. And I haven't fully fleshed out this argument. I think it's intuitively clear that invertible bases exist because the zero divisors are a space of smaller dimensions, so there always has to be stuff close enough to it. But as you can see, like there's something icky here, and I have had various students claim to me they've proved it, but the harder I poke at their proofs, the more I'm convinced that, But
that it's wrong. Or
my argument in the paper is just this: since we have n linearly independent vectors in an n-dimensional vector space, therefore, applying this procedure iteratively yields a basis. Let's see here. What do I say? I say so the zero divisors is at most n minus 1 dimensional, hence there exist, the ith component is now a unit since the transformation preserved linear independence of the basis so long as Ci is not equal to 0. We know by linear algebra the vectors must also, the span of vectors must also be preserved, since we have,
So we're looking for a basis.
What's this argument here? Maybe there is an argument here. Zero divisors is n minus 1 dimensional. At most n minus 1 dimensional. So there have to be constants, not all 0, such that that is another. I will just say this, Audrey. I at various points in my life can either believe in the proof that's written here on page 12 to 13, or don't believe. And like
So we're trying to find a basis that doesn't hit the 0 divisors?
we're trying to say if we have a basis which hits the 0 divisors, right?
Yeah. You can turn it into an invertible basis.
That we can get rid of the 0 divisors in our choice and trade them for invertible elements in such a way that we still have a basis.
But the problem we run into is that that basis might be a scalar.
Yeah, the problem we run into is if we make our choice poorly, then we could inadvertently choose something that is linearly dependent on the other vectors in the set. So there's an argument which is given here on the bottom of page 12 going to 13, and I believe that is due to Nathan Bedell. And I sometimes understand Nathan's arguments and I sometimes don't. And I mean, he's convinced me in this argument at one point, I believe.
It's on 1213?
Yeah, the proof of theorem 4.17. But I don't know, in my heart I would like to provide a proof which is more explicit. I always felt like this was a weakness of the paper, and I spent a bunch of time on it, and I never got something that I liked more, so I just kind of go on, because it's not that interesting in the big scheme of things, but I mean, this is an important theorem. I rely on it later to build a particular kind of basis, because if I have a basis of invertible and an invertible basis, I can make certain arguments.
Wait. So he says...
What's happening? Someone has thrown a ball.
Wait, can you say that okay, so...
That was the white ball.
One-dimensional algebra.
This is
Hence,
the white
there
part.
exists a C1 through Cn, which is not equal to Ci is not equal to 0.
Here's the white part.
See, this is the light part. We'll show you. You say hi to Mr. Audrick? So you tell him what your name is?
What's your name?
Audrick.
Will you tell him what your name is, Benjamin?
I'm Benjamin.
You're Benjamin. How old are you?
I'm this many.
4.
Sometimes I'm making a tent.
Sometime you're making a tent? Okay.
Why?
Pretty much all the time.
Yeah. Okay, wait. He's saying that if you, on the bottom of 12, he says that suppose there's a basis element wi, which is 0 divisor. Recall that 0 divisors in n-dimensional algebra, most can be n-1. Hence, there exists a C1 through Cn where Ci is non-zero. And so he's saying the Ci is the thing that's very close to Wi, right?
Well, these are constants.
Well, Wi, okay. Well, he says W, okay. Such that C1 W1 to Ci Wi can be a basis for A with ith component. And since the transformation Wi to C1 W to Ci Wi preserves linear independence of the basis as long as Ci is not equal to 0. That wouldn't. Because Wi is still a 0 divisor, unless you're saying that it's non-zero. Because he doesn't claim that Wi is a non-zero.
Well, I mean, he's not wrong that the transformation Wi maps to...
Yeah, but what if Wi is 0?
Well, it's originally a basis. Wi can't be 0.
Okay.
I mean, gamma's a W1 through W1 basis. You are a funny little man.
bases be?
I think the devil's going to be in the details here of the claim that WI maps to C1 W1 plus da 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 plus CIWI plus da 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 plus CNWN.
Yeah, that's
There's
there's something there that I don't. That's funky.
Preserves linear independence.
Yeah, because like, is that provable? Can you prove that that preserves linear independence?
Daddy,
Well,
Daddy,
Because
Mom, I have to show you something, Daddy.
what do you have to show me?
Let's show him something.
You're going to show him something. Maybe you should show us stuff outside. We got to go cook the hamburgers now, okay? Is that the plan?
No, inside. In the living room.
In the living room.
I made something.
You made something in the living room. That does sound exciting.
And you can tell me I just made a bed inside the living room.
Really?